Hello, welcome back. So in this part, we are going to discuss about the modular ratio in compression. Well, basically, I have already discussed about modular ratio in context of singly reinforced beam. So earlier, I have discussed that modular ratio is actually ratio of ES by EC. ES is the Young's modulus of elasticity of the steel, and EC is the Young's modulus of elasticity of the concrete. But because this E value of concrete is very difficult to calculate, so IS code has given the value, the formula of M as 280 by 3 into sigma CBC. Well, this modular ratio will work for tension reinforcement when we provide steel in the tension region. But now as we are talking about the doubly reinforced beam, so in case of doubly reinforced beam, we provide reinforcement in compression zone also. Well, when we talk about compressive steel in the doubly reinforced beam, this modular ratio will not work. Why? Because compressive steel may experience more strain, more stress because of the phenomena of creep. As in the compression zone, concrete is mainly carrying the compressive compression, and as concrete experience creep and shrinkage, so because of this creep phenomena and shrinkage phenomena, the steel in the compression zone will also experience more stress than the tensile steel, and that is why the modular ratio that we use for compressive steel, it is basically, we represent this as M dash, and it is actually 1.5 times of M, this M. So because of the phenomena of creep and shrinkage in concrete, as I said, that steel in compression will experience more stress and more strain. So that is why to account for those excessive for extra stresses and strain, we take this M dash value. So this M dash value will be for uh, steel in compression, while this M value will be for steel in the tension zone, like we have used this in case of singly reinforced beam. So that is all about the modular ratio. So basically, when we calculate the stresses in compressive steel, we will multiply, I mean, in case of equivalent area, we multiply that by M dash value, not by the M value, like we used to do in case of singly reinforced beam. So as I said, creep deformation of concrete produce additional strain in compression steel and gradually raises the level of stress. And basically, to account for this increase in stress, the modular ratio is also increased. And modular ratio for compressive steel is basically denoted by M dash, and it is taken as M 1.5 times of M. And also, IS code also has recommended that the compressive stress in steel in compression zone is calculated by multiplying the stress in surrounding concrete by 1.5 M. So IS code also has recommended that we will multiply by 1.5 times of M, not by M, but 1.5 times of M, so that we can get the actual stress value in the compressive steel. But at the same time, that actual stress in steel should not exceed the permissible stress, which is sigma SC. So till now we used to discuss sigma ST. So this sigma ST is permissible stress in tension. Now we are talking about sigma SC. So this sigma SC is related to the permissible stress in the steel in the compression zone. So now we will start the new topic, which is analytical aspects of doubly reinforced beam. Now, first we will try to understand using the figure. So in this figure, you can see this is the actual beam, actual doubly reinforced beam. And in this case, you can see steel is provided in the compression zone, and we are calling this as area of steel in compression, which is ASC. Similarly, area of steel provided in the tension zone, it is actually AST, and this AST is actually the sum of AST1 plus AST2. So AST1 is to balance compressive force carried by the concrete, and this AST2 is the area of steel which is here to balance the compressive force carried by the this steel. Okay, so this is the actual beam. Now what we do is to calculate for our analytical aspect, what we do is we try to generalize this actual beam. So basically what we do is, in case of singly reinforced beam also, we try to replace this actual steel bar by the equivalent area of the concrete. So there you can see the area of steel is replaced by area of concrete, equivalent area of concrete, by multiplying modular ratio with the area of steel in tension. So this is actually the equivalent area of concrete, okay, in terms of steel. Now, in case of compression zone now, because we are providing the steel in compression zone also, so we have to replace this compressive steel for equivalent area of concrete. So what we are doing is we will provide equivalent area of concrete in place of this steel also. Now equivalent area of equivalent area of concrete in place of this compressive steel will be provided in context with the modular ratio for compression, which is m dash value. So we will discuss more about this equivalent area in the next part. And this third diagram is showing the stress level in concrete, in steel, in compressive steel also. So this FCBC value is actually the maximum flexural compression in concrete. Similarly, this FCBC dash, so this is actually the actual flexural compression stress in the concrete at the level of steel. So as I said, we will replace this compressive steel with the equivalent area of the concrete, basically for our calculation purpose, not actually. Actually, the beam will look like this, but for calculation purpose, what we are doing is we are replacing steel with the equivalent area of the concrete so that our calculation can be worked out. So I have already discussed about equivalent area in one of my lectures of concrete design concept. So you can refer to that if it is not clear with you. And so this FCBC will be the stress in equivalent area of concrete, and this FST by M is the equivalent stress in the equivalent area of concrete. So we will discuss more about it in the next part. Thank you.